So I'm going to stand. This chair's a bit intimidating. So I was asked actually to talk about the Higgs boson, and the research councils put a lot of money into it, but it may not exist. And I was also asked to talk about dark energy, and the research councils put a lot of money into that, but it may not exist. And I could talk about life on Mars, and the research council put a lot of money into that, but oh come on, where's the audience participation? Anyway, so I thought I would talk about something that we know does exist, which is chemistry. We are bits of chemistry. We are carbon-based life forms carrying out all sorts of chemical reactions, drinking our wine, digesting our food, thinking our thoughts. Don't go there. We are chemistry. And my kind of belief system has got a little bit weaker as I grow older. And there is something called the anthropic principle. And in its strong form, it says, well, the universe has been designed the way it is so that we humans can exist. And then that leads you to a question of whether or not there is or is not a designer. And I prefer the weak form, which is kind of goes like this. We can deduce certain things about the universe because we do exist. So if we are carbon-based life forms, then one of the things we can deduce about the universe is that carbon must exist. Okay, that's fairly basic. Actually, it's quite difficult. How many of you kind of know anything about the Big Bang? Rough indication. No, you don't have to put your hands right up, but a little bit of a wave, something like that. Yeah, that'll do. Yeah, COSY, Right. Okay. So the Big Bang is an enormous, very high temperature explosion, after which the universe starts to expand quite rapidly, and out of the Big Bang you create chemical elements. And in fact, the whole idea of the Big Bang was that it was originally put forward as a way of explaining the chemical elements. Problem is, you form element number 1, which is hydrogen. You form a bit of deuterium, which is heavy hydrogen. You form element number 2, and that is helium. And you form a little bit of element number 3, which is lithium. But by that time, the universe has expanded so much, which is not very much actually, but by that time it's expanded enough that you can't form any of the elements heavier than lithium. So you form element 1, element 2, element 3, but not element 4, not element 5, and most certainly not element 6, which is carbon, which is what we're based on. So here we've got this conundrum. The Big Bang is put forward as a way of making elements. On the one hand, 13 point something billion years ago at the beginning of the universe. And here we are, carbon-based life forms, but the damn thing breaks down before you get anywhere near carbon. So how do you make carbon? Something like 60 years ago, Fred Hoyle, anybody heard of Fred Hoyle? Steady state theory, it was all the rage when I was at school because Big Bang theory was American and steady state theory was British, and we were good British schoolboys, and so we supported the steady state theory. Anyway, that turns out that that's wrong. But Fred Hoyle is a great guy because he had lots and lots of wrong ideas and lots of really insightful right ideas. So he came up with this notion that carbon had to be being made, along with all of the other elements beyond element number 3, in the centre of stars. Except there's still a problem. Because even if you take the very high temperatures and the very high densities in the centre of stars, then the way you would think you would make elements would be, okay, you've got up to, well, 90% of all atoms are hydrogen, so let's start with hydrogen. So you can make helium out of hydrogen, you can make lithium out of hydrogen and helium, because that's elements 1 and 2 combined to form element 3. And you can make element 4, which is beryllium, by banging 2 heliums together, because you're adding helium 2. Helium 2 is element 2, plus element 2 gives you element 4. Doesn't work. Just can't do it. The energetics just don't work out. So if you can't form element 4, how do you get to elements 5 and element 6? Tough. And Hoyle came up with the idea, and he said, well look, never mind about doing it just stepwise. Let's bang 3 heliums together, 3 lots of element 2, and we will form element 6, and it will be element 6 in an incredibly excited state. The nucleus in element 6 will be incredibly excited, and there has to exist a stable, very, very excited state of the nucleus of element 6, carbon, because we know carbon exists. So he used the weak anthropic principle to say, because we know carbon exists, there must be a way of making carbon. We can't make it from element 4 because element 4 is too unstable. Therefore we'll bring 3 lots of element 2 together, bang them all together. Going to be a lot of energy left over. Somehow carbon must be able to absorb this. And he persuaded a guy called Willie Fowler to have a look to see if he could do studies on the nucleus of carbon. And he found, yes indeed, there was a very, very high energy state of carbon that was stable, that would absorb all the energy when you bang 3 heliums together and you make carbon, element 6. And that was incredible, because that was somebody arguing from the weak anthropic principle through to the energy levels of the carbon nucleus, telling an experimentalist, go find this energy level, and the guy found it. And there's a fabulous paper which really takes some reading, so you know, if you're not into cosmochemistry and astronomy, it's a challenge. Burbage, Fowler and Hoyle, 1957, it's the Bible of how we synthesize the chemical elements. So we make the chemical elements beyond element 3, so beyond hydrogen, beyond helium, beyond lithium, anything beyond that we make in the centre of stars. And then very big stars do something that's very helpful. They go supernova and they explode and they pour all these heavy elements all the way up to the elements iron, cobalt and nickel and some beyond that, and they pour them out into the universe, and so we've got the chemical composition that we need in order to make carbon-based life forms like ourselves. Okay? Simple. This is where I get the meerkats out. No. You see, the problem is, how do you make stars? Well, we know how to make stars today, but if you go all the way back to the early universe, when you only had elements 1, 2 and 3, and 90% of all atoms are hydrogen, so you mainly have really, you just had hydrogen, 10% helium and a kind of a sprinkling, like a salt sprinkling of lithium. How do you make stars? Well, okay, that's very simple. Basically, you make stars, you get a big clump of gas, perhaps a bit denser than the gas around it, maybe it's had something to shock it, I don't know, Kate Middleton. And you get this big clump of gas to condense under the force of gravity, which is an incredibly powerful force, especially with large masses and big distances. So, okay, very nice. I guess we've all done that trick with the bicycle pump, where you put your thumb over the end of the bicycle pump and then push it very hard, and your thumb gets hot, doesn't it? Yeah? Because when you compress gas, it actually heats up. And if you actually do the trick, the gas that is escaping flies apart, expands very rapidly, because we also know that hot gas expands. And the problem is that as you bring this big clump of gas together, as it gets denser and denser, it's also getting hotter and hotter. So gravity is pulling together. but the increasing temperature is pushing the particle. So you've got a problem. How do you make stars under that situation? Well, you can cool things down. Up until about 100,000 years after the Big Bang, then all matter was in the form of atomic nuclei, positively charged atomic nuclei, negatively charged electrons, and photons, particles of light that interact with anything that's electrically charged, and so it's all mixed up. And then after about 100,000 years after the Big Bang, the density had dropped enough, the temperature had dropped enough to a few thousand to a few, maybe 10,000 degrees, and neutral atoms in which an electron combines with an atomic nucleus to form a neutral atom, they could form up. And that's good because atoms have a whole series of energy levels, and when you bang two atoms into one another, one atom might lose energy, the other atom will gain energy, and then it'll fire off that energy as a photon, and two atoms effectively have cooled down. So atoms can cool down gas by banging into one another, bang, 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 like that, and it cools down. So you're getting over the problem of getting the temperature of the gas down, but you can't do it enough with atoms alone. You've got to get temperatures well below 1,000 degrees, and atoms will only take you down to about 8,000 degrees. Now, atoms do this, bang, 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 they bang into one another, and the jumps in energy that they can create are quite big. So you need a relatively high temperature to bang one into the other, make one jump up an energy level, and then lose its energy and cool down. Molecules, on the other hand, can do some neat things, and if I had a bit more space I was going to ask for a volunteer, but I don't really have enough space to do this, so I'm going to have to do it solo. So I was going to do a little dance if I had a partner, but most of us guys know that, you know, when we go to a disco we end up dancing on our own anyway, because we're so useless at it and nobody wants to dance. So I'm just going to do this on my own. So molecules can do things that atoms can't. Let's pretend my body is an atom of oxygen, say, and this is an atom of hydrogen, and this is an atom of hydrogen, and if I look like that, I'm H2O, which is, thank you, so I'm a water molecule. And water molecules can do things that atoms can't. They can vibrate, like this, or like this. They're energetic things, molecules, but their energy levels are quite low down. And they can do other things. They can spin around like this. They can rotate. And it's the fact that molecules can do things that atoms can't, is that you're able to cool the gas down enough to make the very first stars. And once you get the very first stars, then you can get over this obstacle of making these heavier elements. So you can get to carbon, you can get to oxygen, you can get to nitrogen, and that means you can have your basic CHON, C-H-O-N chemistry, which is what organic life is based on. Carbon, hydrogen, oxygen, nitrogen, and then sulfur and phosphorus and lots of other things. So you can do this, but it's a real struggle because vast amounts of gas in the early universe, they're only cooling, I mean huge gas clouds, gazillions of kilometres across, are only cooling at the rate of your average electric light bulb. Not very much. They're giving out pretty. One of the things, of course, we've got in astronomy is that we do have time. I mean, even between friends, 13.7 billion years is quite a long time. So, you know, 100,000 years after the Big Bang, well, that's quite a long time. And then going up to, say, 1 million years or 2 or 3 million years after the Big Bang, you're forming stars, you're forming the very first stars. And the very first stars were either very small, in which case some of them might still be around, because small stars live very, very long lives, or they were very big. And very big stars live short lives, and they go supernova, bang, and all the chemistry, all the chemicals go out into a new set of gas clouds that aren't just gas, but they're dust and dirt and all sorts of ice, all sorts of stuff. How many of you have ever actually seen the Milky Way? Difficult to see it in London. Okay, so those of you, how many of you have seen at least pictures of the Milky Way? Okay, so most people have some idea. So you know in the Milky Way you've got a huge swathe of stars, but you've also got dark lanes that run through the Milky Way. So those are the big gas and dust clouds. And it's in those that you get all this neat cosmic chemistry going on. Now, way back in the early universe, and the reason I subtitle my book and my talks and guided to it, when you just had mainly hydrogen, you formed three sorts of hydrogen. You formed atomic hydrogen, molecular hydrogen, in which two hydrogen atoms are joined together, and a molecule called H3+, which is a little triangle of three hydrogen atoms and electrically charged. And it was there right at the very beginning of chemistry. And it will take us all the way through the whole river of cosmic chemistry, right up to the point where we're getting close to the kind of molecules that will give rise to life, simple life forms, and eventually life forms like ourselves. This is an important little molecule in the next phase of chemistry. And the reason is this. I guess we've all done some cooking. And we all know that you've got to, by and large anyway, you've got to heat things to get them to cook. And anybody who did chemistry at school will know that you often had to heat chemicals to get a reaction to go. In those dense gas and dust clouds in the Milky Way, where all of this interesting chemistry is going on, it's cold. 10 degrees, 50 degrees, 100 degrees above absolute zero. So 10 degrees above absolute zero is minus 263 degrees, 0.2 below the freezing point of water, where ice comes. So that is pretty cold. You don't have a lot of heat in these gas clouds. You don't have a lot of energy in these gas clouds. And getting chemistry to go where you don't have much heat is very difficult. But this neat little H3+ molecule, and you've got to remember that we're still 90% of all atoms are hydrogen, so there's a lot of it around, a lot of it forming up. It's very reactive because it's electrically charged. When things are electrically charged, they go chasing after all sorts of other atoms and molecules, and you can start whole chains of chemistry going in these big gas clouds. And it's amazing. There's well over 100, maybe getting on for 200 different chemicals, different molecules that have been discovered in these gas clouds. I mean, they were first discovered really back in the 1920s and 30s, and then when radio astronomy came of age just after the Second World War, it was like, wow, the whole Milky Way is chemical. Galaxies outside of our Milky Way are chemical. We're finding all these damn chemicals everywhere. Alcohol is everywhere. Water's everywhere. You also get chemicals based on hydrogen cyanide, HCN. HCN and water and a bit of mixing around give you amino acids, proteins. HCN and a bit of water give you what are called nucleobases. These are the special little molecules that bind together in RNA and DNA to give you the genetic code. In space, we've been able to detect enormous molecules of just carbon, all chained with itself. Buckminster fullerene, soccerine. I don't know if you've ever seen that wonderful C60 molecule that looks like a cage. It's a cage of carbon atoms shaped like a football, found by Harry Kroto, who used to be at Sussex University and got the Nobel Prize for doing this. These have been found in space. You can make lots and lots and lots of really interesting molecules in the gas. You can do some even neater things, and this is what absolutely amazes me. You can do some really neat things on little grains of dust and ice where it's very cold. And this means making use of a special kind of property of quantum mechanics. So quantum mechanics is the physics that describes the very small. Now, if you imagine that this seat, this is the surface of a grain of ice in a dense gas cloud in the interstellar medium. And, I don't know, a molecule comes and lands on here. And it's very cold, so it's kind of stuck. It's maybe only 10 degrees above absolute zero. And another molecule comes here, and it's very cold. And it's only 10 degrees above absolute zero. And you want some chemistry to happen. Well, they haven't got any energy. They're not going to move close to one another. So what happens? Has anybody heard of the Heisenberg uncertainty principle? It kind of gains a little bit of popular currency because some people believe the Heisenberg uncertainty principle is the physical basis for God-given free will. Well, okay, you can believe that if you want. But what it says is that if I know how much momentum, how much motion a particle has got, if it's a quantum particle, I don't know where it is. So these particles are stuck on the grains and they're not moving, so they have no momentum, very little momentum, maybe they're wobbling a little bit. So I don't know where it is. And the particle is delocalized. So although I think one molecule has landed here and one molecule has landed there, actually it's kind of delocalized over the entire grain, like a kind of blancmange. You know, you put a lump of blancmange down, it kind of spreads out over time. And so as it spreads across the grain, the two can react and they carry out some really intricate chemistry. And we know this kind of thing's happening because we get bits and pieces of space junk coming regularly onto Earth in the form of meteorites. And particularly in 1969 we were visited by two very significant meteorites. One was in over the town of Allende in Mexico, and I think it's the state of Chihuahua, and the other was at a place called Murchison in the state of Victoria in Australia. And these were quite big, you know, they were about the size of a car coming into the Earth's atmosphere at 15 kilometres a second, which is quite fast. Did you see that thing in the metro today about this guy who's clocked doing 152 miles an hour on a motorbike? You go see that? I thought it was a great story. Anyway, 15 kilometres a second is a lot more than that. So, yeah. If you're driving a car at 15 kilometres a second, even if it's coming into the Earth's atmosphere, you're in for a speeding ticket. If you get very hot and you break up, and bits and pieces of rock go all over the damn place. And they've been collected up. And they were collected up very quickly because these were bright. People saw them coming in the sky, obviously. And, you know, lots of this stuff, kilograms, even tons of this stuff, I think, have been collected and distributed around the world. So there's a bit of the Murchison meteorite in the Natural History Museum if you want to go and look at it. And what we found in the centre of those meteorites is amino acids, these nucleobases that can give rise to DNA and RNA, or perhaps not actually the exact ones that give rise to DNA and RNA, but things so very similar that it's a fair guess that you could probably form a lot of these things in space on grains. The grains all clump together. They get turned into asteroids, planets. They bang into one another. Bits and pieces fly off and they come in our direction. You may recall several years ago that there was even talk of a bit of a Martian meteorite having fossil life. Nobody quite believes that now, I don't think. But there's lots of very interesting chemicals come to Earth. So we know that in the chemical cosmos we can form some very, very complicated molecules. The kind of molecules that get usually termed prebiotic molecules. So we've got quite a good idea that all of the chemistry going on in the universe can create building blocks that could turn into life. And we know that these bits and pieces being delivered from outside of the Earth can survive as complicated molecules all the way down to the surface of the Earth. Now, there are other scenarios. People who are not astronomers don't like the idea of things not all happening on the surface of the Earth, and that space has anything very much to do with it. But for one thing, we're pretty sure that all of our water is in space in the form of comets. One reason for that is that if you work out the temperature where the early Earth formed, then you couldn't have had liquid water, and you couldn't really even have had water included in rocks. It would have been so hot that it all would have been driven out. In fact, you don't get to form ice in the early solar system until you get out as far as the orbit of Jupiter, which is about 5 times as far away from the Sun as we are. So how Earth got all the water that we've got, and we know we've got all the water obviously, is a bit of a mystery, except that it looks very much as if it's been created in cosmic chemical laboratories and then shipped to Earth in form of comets. And we also know that other chemicals get into comets, so methane, ammonia, alcohol, acetylene, etc. All kinds of things that can be used to build up life forms like ourselves. So there are problems. Deoxyribonucleic acid, or ribonucleic acid, that's got a backbone made up of phosphorus, phosphates, and a sugar called ribose. And you can make almost all the sugars from a very simple compound called formaldehyde, but not ribose. So if we're trying to understand how we get to life forms like ourselves, we have a problem. We still don't really understand how the backbone of DNA and RNA forms. And it may well be that the very earliest life forms actually used a rather different structure to get something that replicates in the way DNA and RNA do, to give you kind of reproducing systems. We don't even know how one of the bases in DNA and RNA, a base called cytosine. So if you know your genetic codes, C binds with G, cytosine with guanine, and adenosine with thymine, or adenosine with uracil in RNA, and that's the way you make sure that when the two strands of DNA split, they form up with the right pairs so that you get properly reproducing cells and so on and so forth. But we don't know how cytosine works. But we've learnt a lot. As I say, the first molecules in space were only really detected 90 years ago, which is not very long ago. And we only worked out in 1957 how to get beyond chemical element 3 to chemical element 6 and the other elements that make us up. And it's only in the last probably 20 or 30 years that we've worked out how to cool down the gas in the early universe enough to make the stars that you need to make the chemical elements. So I'm quite happy with doing something simple like astrochemistry, because I do know quite a lot. And when I talk to my cosmology friends, and they say, well, actually 75% or 76% of the universe is dark energy, and 20% of the universe is dark matter. So Steve, you're only studying 4% of the universe if you're doing cosmic chemistry. But then at least I know that 4% exists. Thank you.